So good afternoon, everybody. It's a pleasure that I can give you here a small impression of the research work or part of the research work that is done at the Astronomical Institute of the University of Bern. It is the work of the so-called research group on satellite geodesy, which I try to put here in some pictures. So we are mainly working with so-called GNSS. These are global navigation satellite systems. And the most famous one is, of course, the US-American GPS, the Global Positioning System. But there are also others that we are analyzing. So, for example, the Globalnaya Navigaционная Sputnikovaya Sistema, which stands for GLONASS, or the Russian panda of the US-American GPS. But there is also the upcoming European Galileo system, and there is also the Chinese system, which is upcoming. And all these data are analyzed in our institute on the UBELIX cluster of the University of Bern. So this is the link a little bit to this talk with this meeting here. So just a couple of work, how GNSS work. I guess most of you know this. Therefore, very briefly, there are several satellites. They transmit signals which contain information about the distances between these satellites and the ground receiver antennas. If you know the position of the satellites and also clock information, you are able to derive position information of these ground antennas. And these receivers are very popular nowadays. They are in all the handies, smartphones, navigation systems that you have. Typically, they look like this. They just provide position information, but this triggers a large number of various applications. Just mentioned some of them. You see here a couple of pictures. That's maybe the most famous part of GPS, as it is known for everybody, I think. Well, maybe not that well known is what can also be done on a scientific point of view out of these data. There are also other receivers. Scientific receivers, they look a little bit more bulky, they are a little bit larger, and also the antennas look a little bit different. And they are very interesting because they are able to provide measurements on the millimeter level, which allows, of course, for much more precise applications. And this makes GNSS to a very interesting tool for geodetic applications and, of course, then also geophysical applications. So there are many different networks. So there is, for example, a local network in Switzerland and also global ones triggering many different type of scientific investigations. But all these applications need something. They need very precise satellite orbits, for example. And you may ask the question from where they come from. Well, part of them comes from our institute, for example. So I will just try to sketch this. This is work done in the frame of the so-called International GNSS Service. That's an idea which has been born in the 90s and started to be an official service of the IAG, the International Association of Geodesy, since 1994. And the IGS receives contributions nowadays from about 300 institutions worldwide, located in 80 different countries about, and all this is done on a voluntary basis. So that's the nice thing. Users do not have to pay for these high quality data products. It's done on a best effort basis in order to support science and corresponding applications. What is part of the IGS? These are the tracking stations, then there are data and product centers, and eventually there are analysis centers. And our contributions from the University of Bern are twofold. The less important one maybe are that we also have some own GPS antennas. They are located here at the fundamental point in Switzerland at the Zimmerwald Observatory nearby Bern. But most importantly, we are running a so-called global analysis center of the IGS. And this is called the Code Analysis Center. There are just 10 of them, and the purpose is, I will just tell you, to derive several products for the IGS. So CODE stands for Center for Orbit Determination in Europe. It's a joint venture of several institutions, mainly from our institute. We are running and hosting this analysis center, but it's in collaboration also with Swiss Federal Office of Topography, for example, or the German PADA, the Cartography and Geodesy Agency, and also a university institution in Germany. So What is done? A lot of computations are done, of course. Therefore, we are speaking here quickly about this. For this purpose, we are needing software. Well, unfortunately, GNSS data analysis is not just something where you can buy a package in a store that fulfills all your requirements. Therefore, our institution has started developing its own software packages many, many years ago. So this is a project running for decades already. It is the so-called Bernese GNSS software, where first developments have been started in the 80s, actually. Nowadays, this is a state-of-the-art software package which is used worldwide by, in the meantime, more than 600 institutions. So it's a very important product for us to sell also to the interesting users. And it is used by mapping agencies, by agencies for cartography and geodesy, and so on and so forth. And of course, also it is used by ourselves for our daily work. And our daily work, I try to summarize this in a little bit in a couple of slides. So we have here the main product, maybe. These are really the GNSS orbits. So the entire constellation is derived by these number of analysis centers. There are about 10, let's say. And all this started, as mentioned, in 1994. And you see here in this graph, without going into details, how the quality of these products has improved over the years. Starting in 1994, orbit qualities were at the level of about 20 centimeters maybe. That's already very good, of course, because before this was much worse, where there was no coordinated effort to derive these things. And nowadays, all the analysis centers have improved their methods, better background models are available, and the consistency nowadays is better than about 2 centimeters. In order to derive these products, we need a lot of data. They are collected every day and continuously by all the global tracking stations of the IGS, by this global tracking network. There are several hundreds of these stations, and all these data are analyzed routinely every day at our institute on the UBELIX cluster in order to derive all the different parameters of interest. So one parameter would be, for example, the station coordinates, to derive them every day, for example, out of these millimeter precise measurements. If you do this, and if you do this over very long time spans, then you are able, for example, to determine, so to say, as a byproduct, also things like the movements of the station, so plate tectonics, for example. What you see in this graph here is the different plate motions. Every arrow here is one station, and you see, for example, here in Switzerland, that Switzerland is moving together with the rest of Europe on this Eurasian plate with a magnitude of about 3 centimeters per year. This is routinely measured with very high precision with GNSS data. But there are also many other things, and it's always interesting to analyze, of course, spectacular events. Also, this is a very sad one here, of course. So just to give you a flavor about the sensitivity when a large earthquake is ongoing, like, for example, the large one in Japan in 2011. I guess you all have seen all these pictures in the news channels. And what GNSS saw first, of course, very large displacements in Japan, but I will now just show a movie where you see how this wave of the earthquake is expanding. So here you see the incident of the earthquake. So this is the timeline which is moving, and here are the displacements, and now here you see how this wave of the earthquake is moving for 1,000 and 1,000 kilometers. And if you follow here, then you see the small displacements even up to here. These are stations 5,000 kilometers away. So even 5,000 kilometers away, several times later, still very small displacements could be measured by GNSS, thanks to the very high precision, of course, of these GNSS measurements. If you just would have analyzed this one here, then you would have concluded, well, the receiver has derived measurements of inferior quality, something like this. But of course, with the entire history here, you see that this is clearly related to this very large event, of course. Other things that have to be co-estimated with the station positions and the orbits are, for example, parameters defining the orientation of the Earth. So what you see here is the movement of the Earth's axis in the Earth's fixed frame. This is a bad circle, so to say, with a diameter of about 15 meters on the Earth's surface. So that's the situation, how you would look like it at the pole, so to say. And that is something that you can determine very precisely nowadays with GPS data. And this is also done every day, so with sub-millimeter precision you can pinpoint on the Earth, so to say, where the Earth's rotation axis intersects with the surface of the Earth. There is a lot of interdisciplinary science in principle which can be done with GNSS data. The reason is very simple, because the signals are transmitted from a satellite, they are received from a ground station, for example, so the signals need to pass through the Earth's atmosphere. This means there are delays of the signals in the Earth's atmosphere, and by studying these delays one can also say something about the properties of the Earth's atmosphere. So it's possible to estimate tropospheric delays, and if this information is derived quickly enough, so let's say within less than 1 hour, then this is very interesting for weather forecast, for example, and it's actually also used. So nowadays it's more or less routine that all the meteo agencies use GPS data in order to feed these information into their weather models. But there are also other parts of the atmosphere which are passed, so the little bit higher levels, so the ionosphere, for example. The ionosphere is the place where free electrons are, and this is also causing signal delays, and based on this one can derive the ionization in these layers and can derive here these maps of the ionosphere. You see here this bulge which is basically co-rotating with the sun around the Earth. So things that are annoying for some type of applications, they are very interesting for other type of applications, because there are of course atmosphere specialists which are then interested in these things here. Just to highlight a little bit the requirements from the IGS sites concerning these data analysis. So there are different ways, so to say, which are interesting. There is one requirement that results must be quickly available, and for this purpose there are so-called ultra-rapid products which are generated with just a latency of 3 hours time after the last observation has been collected. And this is something which is generating on the Obelix cluster here at the University of Bern a certain load, because several of these ultra-rapid products are updated every day, more or less continuously, in order that the near real-time community of these products has their valuable source of information. On the other hand, there are applications which require the most precise results, most accurate results. For this purpose, one has more time. There is a final product line which is generated typically with a delay, a maximum delay of about 2 weeks, where one has more data to process, a little bit more refined analysis methods maybe that are adopted. And just to give you a flavor about the number of stations for these different product lines, the number of observations and also the number of parameters you see here for such an ultra-rapid, which has to be produced very quickly. There are a little bit less than 1 million of observations and about 14,000 of parameters which are estimated, which are consisting of the orbital parameters, the station coordinates, Earth rotation parameters, troposphere information, things like this. And typical situation, if the people from the Obelix cluster are monitoring the load, they would maybe see over the night from our institute something like this. This is a typical final processing. This is just the number of jobs. Some of them are very small. There are a lot of small jobs, for example, related to the data download or things like this. Then there are actual processing jobs where a lot of equations have to be solved, and this is going on every day like this. And this is just here the final processing over the night. So during day we have, for example, in the early morning hours we have rapid processing or then ultra-rapid processing. Just one thing which is important for us, this is the reliability, the availability of the nodes, and that everything is running smoothly. So for example, in particular for these ultra-rapid products, we need to be in time, and if we are not in time, then the submission fails, so to say. And what you see here, it's just a statistic for a little bit more or for just 1 year. You see here that for a total of 1,478 ultra-rapid submissions, just 4 of them were not in time. So this gives for this particular year here a reliability of 99.7%. And this is important. Not all of the analysis centers are able to fulfill this. And this is partly also thanks to the very good support that we get here from the informatics division, really maintaining the cluster and making it available for us that we can really use it. Okay, so the last part now, I would focus a little bit on just one special application, which is a very fascinating one and also a little bit a demanding one in terms of resources. Unfortunately, these couple of videos are not all working, therefore I have to explain a little bit more. Somehow it's working, but then it's stopping. So the idea is very simple to be explained. So GNSS satellites are about 20,000 kilometers above the Earth's surface, but there are also many other satellites, lower satellites, so-called low Earth orbiting satellites, typically at altitudes of a couple of 100 kilometers. And you see here a couple of pictures of them, and these are all equipped with onboard GPS antennas. So this means these satellites are also receiving the GNSS signals, and therefore they can be positioned very precisely, typically with centimeter accuracy. And this is, of course, a very, very nice way to continuously monitoring the actual flight path of such a satellite very precisely. So this satellite is like a test mass, like a perfect test mass that can be followed with very high precision. And based on this, one tries to infer some information, for example, about the irregularities in the Earth's gravity field. So what you see here is such a picture of the Earth's gravity field. It's not a very high resolving picture, but a nice animation at least. What is shown here, color-coded, are the deviations of the so-called geoid. That's the equipotential surface, coinciding best with the oceans of the Earth with respect to the Earth's ellipsoid. What is red and what is blue here are the deviations from this rotational ellipsoid. This is about plus minus 100 meters. And this is a way of illustrating the Earth's gravity field as one would like to derive it from these dedicated satellite missions. And there are several techniques, and two of them I will quickly explain. The first one is really extremely closely related to GPS data analysis. So the data from the GPS constellation are used to derive very precise orbits. So the true orbit here, which might be very complicated, is monitored with a couple of centimeter accuracy. And then this is compared with what one would expect based on the best knowledge, so to say, that one has. So this is the computed orbit, and based on these differences, which are monitored by GPS, one tries to improve missing parts, so to say, of the Earth's gravity field. This is complicated, illustrated here by these mountains. Of course, the satellite is not flying that low as illustrated in this graph here, but nevertheless, this one here, which is plotted here, is one of the most recent ones. This was a very low Earth orbiting satellite, just 250 kilometers above the Earth's surface. That's the lowest satellite that ever flew for that a long time in this region, because it was actively maintained at that orbital altitude. And I spent here just a couple of words on this. This was the so-called GOES mission, that's Gravity Field and Steady State Ocean Circulation Explorer, where our institute was part of the so-called GOES high-level processing facility and actually responsible for the official precise orbit determination of this ESA mission. It's an ESA mission. And this has all been done on the Ubelix cluster here during 4 years of the entire mission lifetime. And I do not give you here much more details on this, just the spectacular end, because it's really spectacular. So as mentioned, that the orbital altitude was very low at the very end of the mission, 225 kilometers, and that someday, 4 years after the launch, the fuel was empty at some point. That's clear. That always happens at some point. And then everything went really quickly. You see here the decay of the orbital altitude. Within 1 month, the orbital altitude significantly decreased. And until the very last day, so to say, 10th of November 2013, this was at a very, very low altitude of 130 kilometers. There was the last GPS measurements collected. So until the very last day, one can precisely follow this orbit. And then everything went really quickly. So just a couple of hours later, at 80 kilometers, the satellite eventually broke up and was destroyed in the atmosphere. And just by coincidence, there was even somebody on the world watching at this event. So this is really a coincidence, of course, because this happened nearby the Falkland Islands here. You see here the last pass of this satellite. And just by coincidence, there was a photographer on the Falkland Islands taking pictures of penguins, actually, and he witnessed in the sky what was actually going on. You see here this spectacular picture where you see the breakup of this satellite. Okay, so this satellite, the data were used and processed at our institute. There are also other data which are more sensitive, which are dedicated just to the purpose of gravity field research, and which is at the meantime old mission, still in orbit. It's the Grace mission, a US-American, a US-German mission operated by NASA, where very spectacular inter-satellite measurements are performed. So there are microwave signals exchanged between these satellites, and these microwave signals have extremely high precision. So they have micrometer accuracy. And micrometer is very small. That's the diameter of a human blood cell. And with this microwave technique, it is possible to measure these inter-satellite distances with this very, very high precision. And that's very fascinating, because if this pair is flying here over a large mass anomaly, so the Himalaya, for example, then the first satellite will be attracted a little bit stronger, and then the second, and this induces very tiny distance variations. And these very tiny distance variations can be measured thanks to this inter-satellite link, and allow it to map this back, so to say, on the inhomogeneous, on the Earth's gravity field. And even more, with this, it is possible to monitor even the variations. So the variations are nowadays in the context of global change, climate change, very important, because mass changes are occurring that are not natural. So for example, over Greenland or over Antarctica, ice is melting, and if ice is melting and it's no longer present there, then the attraction is slightly different, the attraction which is felt by the satellites. And actually this can be measured in orbit, and is nowadays one of the most reliable ways to globally assess these changes via the orbital perturbations, which are monitored very precisely with such measurements. So the modeling of these gravity fields in principle is very simple from the mathematical point of view. So it's a spherical harmonic expansion up to certain degrees, and this triggers the number of solved for parameters. And I did not mention all of the different techniques here, just the first two. But typically one is somewhere between degree 100 and degree 200, ranging in the number of parameters somewhere between 30,000 and 60,000. Just to show you, if one includes other data, which is not done at our institution, because we are an astronomical institute and we are not measuring surface gravity data, for example, one can go much higher, and this gives them terribly large systems of normal equations which would have to be solved, because if you translate this, so to say, in sizes of these matrices, assuming that here really the full matrix would be stored, then this gives very quickly very large numbers, of course. And even in this frame here, when we have degree 200, there's not just one system that is set up. There are a lot of them, because you are doing this for every orbital arc that you are estimating. So you can easily fill up disk space very, very, very quickly, of course. So far we were rather comfortable, because we were rather in this regime here, never in this regime, towards this regime here. But there is one mission which makes us a little bit trouble, so to say, because there it's somehow needed to go much, much higher. And this is the last part, which I would like to quickly mention here. There was the NASA mission Grail around the moon, a very spectacular mission, very similar to the Grace mission. In fact, the measurement principle is a copy of the Grace mission. So the only difference is the absolute positioning is not done by GPS, because there is no GPS on the moon, of course. So this is classical radio tracking from the Earth. But in between these two satellites, also microwave signals are exchanged. And again, these are micrometer precision signals. And the most striking difference of this mission with respect to the Earth orbiting satellites is that this mission can fly much, much lower. So on the moon there is no atmosphere. There is no need that satellites need to fly at 400 or 500 kilometers. This mission actually flew at about 50 kilometers during the primary mission phase, and as low as between 15 and 20 kilometers in the extended mission phase. So just imagine, this is 20 kilometers, that's double than an airplane is flying above the surface of the Earth. So it's really very, very low that this mission was flying around the moon. Not very long, unfortunately. It was a very short mission, just 2 measurement phases of twice 3 months of measurement duration. But the anticipated result is that this will give you the most detailed view of the lunar gravity field ever, because also the far side can be measured very precisely, which was so far before this mission never possible. But the drawback is, if you really want to exploit these data, then you need a lot of these parameters. And this is currently a little bit our problem, so to say. So we are processing these data. Everything is rather fine, but we have not yet really achieved this very huge resolution. That, of course, would be nice in order to achieve much better resolutions than shown here. So this is just such a picture of the gravity anomalies of the moon that we see here. So this is not the picture of the topography. That's really something which came out of the gravity field derived via the orbit perturbations that are sensed by these large mass inhomogeneities. Okay, so this brings me already to the summary. I hope that I could give you a short insight of some of the work that we are doing at the Astronomical Institute. One of the main focus, which is closely related to using the Obelix cluster at the University of Bern, is the analysis of GNSS tracking data and also dedicated data from gravity missions. They all provide, of course, huge amount of data. There are some inverse problems that have to be solved. Large equation systems need to be solved for this. All this is done on the Obelix cluster, and the requirements that we have there on the Obelix cluster, they are really very manifold, I would say. On the one hand, we have processes where a lot of small jobs, but a large number are submitted, where we have tight requirements concerning the deadline, so to say, to meet for all these submissions. And then we have also some jobs which are quite large concerning the memory consumption. Nevertheless, there we are of course very happy if this can be efficiently done, because we would like to do many experiments. As you can imagine, one does not just want to set up one system to derive one solution, but many of these systems, and this is a little bit the challenge that we are currently facing here with the Grail mission. And this is perfect timing, so anyway, I'm just over with my presentation, and thanks a lot for your attention.